Hi there, Jeff Rideout from Memorial University bringing you a few more Matlab essentials. Going to continue with the projectile motion example that was discussed in the earlier videos. In this video I'm going to discuss how to use while loops instead of for loops to solve this problem, and then I'm going to get into how to save the results of your simulation, how to save those variable arrays into a file so that you can load them into memory again later. I'll talk about how to look up values and interpolate from your saved data, and then I'll introduce Matlab's curve fitting tool. So in a previous M file, we implemented equations to plot the vertical position y and the velocity v of a projectile thrown upward off of a building, say, with the initial height y0, and given an initial speed v0. So here are the equations with which you're probably familiar. I've used open within my editor window to open up the yplot.m file that was previously generated. And it takes 100 time points from 0 to 10 seconds, and it calculates y, the position, and it calculates velocity v. I can run this either by pressing the green play button, or I can go to the command window, and as long as yplot is in my present working directory, I can just type the name of the file without the .m extension. I just chose 10 seconds arbitrarily. The projectile starts at 10 meters and it goes up, and then it hits the ground after only a couple of seconds. But this particular simulation just keeps calculating the position as if the ground wasn't there, and we can see that after 10 seconds, if we took the ground away, the projectile would be over 400 meters underground. Maybe we want to simulate this so that we stop automatically approximately when the projectile hits the ground. So while y is greater than 0, we'll keep calculating the position, and then we'll increment the time and we'll calculate the position again. And then when it hits the ground, we'll stop. Right? So that's why a while loop is sort of an obvious choice here. So I go back to my editor window. I've started a new M file. I've commented it, and I've closed all current plot windows and cleared all variables. I've put in the initial values of the height, the velocity, and the constant acceleration. So a while loop. The initial problem statement was on page 6 of the accompanying document, and the program I'm going to generate is on page 10. All right, what do I want to do here? I want to use a while loop. So the core of the while loop is basically going to be while y is greater than 0, so while the projectile is above the ground. I hit enter, and I go into the while loop, and you can see the smart indentation that happens. Everything that's in the while loop will be indented just a little bit. So while y is equal to 0, y is going to be equal to y initial plus v initial times time plus 0.5 times the acceleration times t squared. This is simply the projectile equation. Now, a couple of problems here that you may be anticipating. In the earlier for loop version of this, we defined 100 time points. We had an array of time points. We took each one and we found the corresponding value of y, and we wrote that to an array, and we ended up with 100 values of y, so we could plot those against time. So we thought of time as a vector. So what's the time right now? How do we do it? We don't need to we don't need to set up an array of time points. We don't know how long this is going to take. That's the interesting part of this. What we need to do is we need to initialize the time by saying we're going to start at time t is equal to 0. All right, so t is 0. So in the first iteration of this, in the while loop, we will calculate position based on the current value of time, which is 0. And then we, assuming that we're still above the ground, we want the time to increase by a certain amount. So I could increase it by 1/100th of a second. This line of code says the time value is now going to be the old one plus 0.01 seconds. And then we will end the while loop. Now I'm going to try to run this by pressing the green play button. Right, because this is a brand new M file, it's going to ask me to save it with a certain file name. I'll just do while test. Don't save any of your file names with names that are Matlab commands, otherwise it'll get confused. I'll just do while test, save it. When I run it, I hear the Matlab error message in my ear. And when I go back here, it says there's an unrecognized function or variable y. As we've seen with error messages before, we can click on the command window error message and it'll bring us back to the line where the problem is. Okay, so it needs there to be a variable y declared before we can determine whether or not y is still greater than 0. Okay, so while y, the first thing it's going to ask is what is y. So I'll go back and I'll say that y is equal to yo. So I'll initialize it. Now I'll try running again, see what happens. Okay, I did not get an error message. And now when I go to the command window, I can look over here on the bottom left pane and I can see that I have a time of 2.04. I have a scalar time variable, which is at 2.04 seconds, which is presumably the time it took for the projectile to hit the ground. And the y value is minus 0.063, which is very close to 0. And the reason it's not exactly 0 is because in my M file, I was incrementing the time by 1/100th of a second. If I were to increment it by 1,000th of a second, I should get a finer resolution. Okay, it'll take a little longer to run, but when it's done, now the y value is 0.0034 to the negative. But you'll notice that I don't have a time vector and I don't have a y vector, so I can't plot t versus y. And a common mistake I see among students is they won't be aware of this and they'll try to plot t comma y because they had a M file which had t and it had y and they didn't get any errors. And when you plot t comma y, what do you get? It looks like nothing. It's actually not nothing. There's one point somewhere on this plot because we're not plotting two vectors. We're plotting one point against another point. So what do we need to do to vectorize our response here? Well, we should, every time we increment the time, we should add to another vector that's all the time values sort of joined together in an array. I'll call that capital T. I'll say the ith value of capital T is equal to the current value of T. Now the problem with that is that we don't have an index I because we didn't use a for loop where we said let's take I and go from 1 to 100. So we need to put an I in there as well. Every time we increment the time, we could increment an integer counter I. So every time we go to another time, we're going to add another value to I. So it'll be 1, 2, 3, 4, 5. And because we want to write a value to this vector initially, I should say that I is equal to 1 before we hit the while loop. Now there's a first I value that we can use to write our first capital T vector element. And this I value at the end will tell us how many steps it took during the while loop before the while loop terminated. So I'll press run again. I'll go back. And now I can see that I have a capital T value which has 2027 double precision entries. And I have a y, well, I still only have a scalar y vector. I can see that it took 2028 steps at 1/1000th of a second for the simulation to end when the projectile hit the ground. So let's go back to the editor. Let's now make our output vector y. I'll just say that y, capital Y, the ith element, is simply the current value of y. All right, that should get it done. I will run. I will go back to my Matlab command window and I'll see that I have 2028 values in the y vector and only 2027 in the t vector. okay? So if I wanted to, that's because I didn't start counting. I had an initial value of t, but I didn't have an initial value of y. So maybe the better way to do this would be, let's see, if I put y I equals y up above a bit, yeah, I'll put it up here before I increment the counter. Okay, now this should work. All right, so I'm taking the first value, I equals 1. I'm writing a time vector and a y vector. Then I'm doing the counting. Okay, so that's the problem I had before. I was incrementing my counter in between the calculation of time and the calculation of y. So we do this, we run it again, and now I can look at my little variable pane on the lower left, or I can type whos, and oh, I should have had correct size. Let me try this again. While test. Okay, now I've got 2027 of each. So now I can plot capital T and capital Y. And I can see that it goes from its initial height of 10, goes up a little bit, falls due to gravity, hits the ground at approximately 2.05 seconds, and ends there. All right. I want to point out something about plotting. If I wanted to plot another curve on the same graph, let's say I wanted to do plot t comma y squared, or I should say maybe just 2 times y. All right. Get the plot back on the screen here. If I just type plot t 2y, what it does is it erases the previous curve that was on the figure. And now you can see I start at 20 and I've doubled the output, but it's erased the previous curve on the plot. If you use the hold command, if I say hold on, and then I go plot, I'm just going to type the first few letters of the recent command and start hitting the up arrow, and it'll take me through the previous commands that used those first few letters. Now I'm going to plot t comma y after I put hold on, and I think I will change the line color. I'll make the line color red. Now I'll go back to my figure. And now you can see that with hold on, it'll let you overlay a number of curves onto a plot. All right, so we've got a while loop as an alternative to a for loop. Now suppose I wanted to save this data to a file. Okay, let's suppose I want an output file that has the capital T vector and the capital Y vector. I'm going to use the save command. I can do help save. I can get all kinds of documentation. There's a lot of different possible arguments for this one. I'll show you a simple form that I use. The easiest way to do this is to first take the 2 individual vectors, the time and the position, and put them into a single array. So I'm going to define a new variable called ty, and I'm going to say that ty is a vector consisting of e prime, which is going to give me a column vector of all the time values. See, if I just type capital T, I get the variable values on the screen, and it's a row vector. If I do T prime, I get a column. If I do Y prime, I get a column. All right, so I want to do a, 2027 by 2 array of variables. So I'm going to say that ty, the variable I'm going to save to a file, consists of square bracket, capital T prime, and then Y prime. There's my 2 columns. So I'll type save. I'll put t and y dot dat. Oops, sorry. I'll put t and y dot dat in a single quote to indicate that this is a string file name. A space, then the variable that I'm going to save to the file, which is ty, then a space, and then ASCII to indicate that it's an ASCII file. All right, I got no output from that, but if I do ls to list the contents of my current directory, I'll see that I have, amongst all this other stuff, t and y dot dat. So it's written it successfully. Okay, now if I clear all, and I do whos, I've got no variables in the workspace. If I want to load this variable in, I can do load t and y dot dat. Okay. Now it puts a it puts a variable t and y into the workspace. The variable name is not t and y dot dat, it's just whatever the file name is, not including the dot dat extension. All right, so now I can type t and y, and I get back the data that I saved. Suppose I wanted to use this as a lookup table. All right, so I'm going to use the interp1 command. Now, if I look at my variables in the workspace, maybe I don't like having this clumsy variable name t and y, the first column of which is time and the second column of which is position. So I'll say that t is equal to t and y, everything comma 1. And then I'll hit the up arrow because I want to type in a similar command. I want to define y, which is the second column of the t and y variable. Okay. So now I want to interpolate. So if I type ty, I should get, there's my vector. Let's say I want to look up the value at, I want to look up the height at 2.0105 seconds. Okay, there's no value in the table for 2.0105. It's going to be in between this entry and this entry. So the height should be somewhere between 0.248 and 0.233. So we'll use the interp1 command. Now, in certain fonts, the 1 looks like an L and it looks like interpol, which seems like a perfectly reasonable name for the interpolation command, but this is actually interp1, because I believe there's a number of interpolation algorithms. So interp1, I want to look up a table that has t and y. I want to enter a t value of 2.0105. So the number I enter in here is the number in the first column, and it's going to interpolate the second column to give me the appropriate value of y. So it gave me 0.2407, which is in between 0.248 and 0.233. So this is how you can look up and interpolate from the values in a table. So if you have a table of experimental data, you want to, and then you come along with another value of the independent variable, you can look up by interpolation what the corresponding y value will be. I've shown you how to plot this t versus y with the plot command. There's also a suite of curve fitting tools, cftool. So that opens up a curve fitting graphical user interface. Now I can select data to fit curves. All right. So this is pretty intuitive. I can say X data. If I've got variables in memory, it'll let me pick the variable that I want to have on the x-axis. So I'll take t for the x-axis, and I'll click y for the y-axis. And what I have here is, in black, I have the actual data points. And there's a lot of them, 2,000 of them. That's why this looks like a thick line instead of a bunch of individual markers. And then I have a blue line, which looks like an appalling attempt at a curve fit. And it's not Matlab's fault. It just defaults to a polynomial fit of degree 1, which is, of course, a line. I know that this is a quadratic curve, right? Y is a function of t squared. So if I choose a second degree polynomial, quadratic, it should give me a nearly perfect curve fit. And you can see it gives me an r squared value, which is amazing. And it gives me an equation for the curve fit, which is the function f of x, which is y, is, well, it's p1, which is minus 4.905 times the x value squared. So in our local parlance, that means minus 4.905 times time squared, because time is x, plus 5.01t plus a value which is 9.995. This is very, very close to within numerical tolerances to the original equation describing the motion. We know that y is y naught, which is 10, pretty close to 9.995, plus v naught t, and the initial speed we set was 5 meters per second, plus a half at squared, a half acceleration is a half of minus 9.81, which is minus 4.905. So in this little benchmark exercise, we can see that our curve fit tool gives us back the expected curve fit parameters, and you can see how intuitive it is. If you wanted to plot a surface, if you had x and y data, that gave you a z, so two independent variables giving you a response z, then you could plot a surface with any of a number of linear or other polynomial curve fit methods. So it's a very versatile tool. Access it with cftool. Okay, so now we can open M files. We can execute logic using things like for and while loops. We can manipulate the data that comes out of the M files. We can save it, reload it as its own data file. We can interpolate, and we can plot.